Okay, so the input to the single source shortest path problem is like this. Say we have a directed and a weighted graph. Weighted means that we have the weights associated with all the edges. So here in this example, the weights represent how much time do you need to spend on the road that connects two cities. And so this is the input graph, and then we are giving a source node. Let's say this is our source node. New York is our source node, and so the single source shortest path algorithm is going to be able to find the shortest path from New York City to all the other places. Okay, so again, the output is the shortest path from the source node to all the other nodes in the graph. Okay, and actually, this is what most navigation softwares use. Okay, most navigation softwares use this. So they are giving a source and destination, and then they're going to start search from the source until they reach the destination, and then they stop. So basically, it means that they find the shortest path from the source to the destination, and then presents the best route for you. So this problem is widely applied. The solutions to this problem is widely applied in real world, and is the problem definition clear?
Yeah.
Okay, cool. So then if I present this problem for you, some of you may relate it to the BFS algorithm, because if we look at the output of the BS algorithm over here, so BFS algorithm also has a source node, and it outputs the shortest path from the source node to all the other nodes, right? It outputs the shortest distance from the source to all the other nodes, correct? So here we can say that from the source node, at the end of the algorithm, we learned that the shortest distance between the source S to this node Y is 3, and then this is the shortest path. So can we apply the BFS algorithm to solve the single source shortest path problem?
Yes, we can.
Yes, we can. Any other answer?
No, we can't.
Why we can't? So the answer is definitely no, we can't, because if we can already use if BFS can help us to solve the problem, then we will not learn this topic. Where I'm just going to directly say, okay, we can use BFS to do this and that 2 weeks ago. So the answer is we can, but why we can't? Do you see the difference between this input graph and the input graph of BFS?
Oh, is it because it's undirected, or like there's more than one direction?
Okay, so yes, here in BFS the graph is not directed, it's undirected, right? But in the single source shortest path algorithm, the graph is directed. What else? Is there any other difference?
Are there like different distances between each nodes?
Yes. So here you can see that the input graph for the BFS algorithm is unweighted. So we say the minimum distance from S to Y is 3 because we need to go through 3 hops. So we basically treat each edge, say that we think each edge is basically the same. We need to travel the same distance for each edge. But in single source shortest path, the input graph is weighted. So it means that even though they're giving 2 different roads or 2 different edges, they may have different meanings. Say road A takes 1 hour, whereas road B takes 3 hours. So we need to differentiate them. So the main reason that, so even though BFS seems to be able to help us solve the problem, but it cannot work. It does not work. The main reason is this: single source shortest path. SSP meaning single source shortest path. Okay, in the BFS, the algorithm, the input graph is undirected and unweighted. Whereas in the single source shortest path algorithm, the input graph is directed and weighted. So we cannot use BFS to solve the single source shortest path problem. Make sense?
Kind of. Can you go over the concept of weight again?
Okay, so the weight means that we need to consider, okay? So for example, if there is a road from New York to Newark, it may take you 1 hour. But if there is another road that directly connects Newark to Miami, this road may take you 18.5 hours. So even though we got 2 roads, but they just have different length, or we need to spend different amount of time on them. So we cannot treat them uniformly. And if you are still not clear about the weight, so you probably need to go back to our lecture with regard to minimum spanning tree. I think I spent like 15 minutes to explain the weight in the minimum spanning tree problem. So you can go over that lecture again. So so here I'm just going to make it relatively clear. Okay, so if we apply BFS to this input graph, do you know what it will output? It will say, okay, the minimum distance from New York to Miami is 2. Okay, 2 comes from this road, So because this road, so this route takes 2 hops, but it does not consider the specific amount of hours that we spend on the roads. So that's why we don't apply it in practice, or we cannot use BFS to solve the single source shortest path problem. Okay, and so as I said, as I listed in the slides, so the limitation of BFS is that it only considers if an edge exists or not. It's basically a binary thing, exists or not, but does not consider the weight or the actual time or length or distance we need to travel for each edge. So then we need a better solution to find the shortest path for a single source problem. Okay, so and here before I present so to solve the single source shortest path problem, shortest path problem, there are 2 algorithms. The first one is named Bellman Ford, and the second one is named Dijkstra. So we're going to learn the Bellman Ford algorithm today and leave Dijkstra to this Friday. And both algorithms are very important. Both of them are very important. So here, so before introducing the Bellman Ford algorithm, I want to introduce 2 simple.
I'm in class.
I want to introduce 2 relatively simple auxiliary algorithms, meaning that we're going to, in our Bellman Ford algorithm, we're going to call these 2 functions, but these two functions are relatively easy or lightweight. So the first one is called, the first algorithm is called initialize. So initialize means this. So the initialized function takes 2 parameters, G and S. So what does G represent? Guess what does G represent?
Starting location.
No,
Okay.
it's the graph. So G is the graph and S is the source node. Okay. So what this algorithm does is that, so for each vertex that is a part of the graph, it will associate with an infinity D and a nil pi. So what does D and pi stand for? What does D stand for?
Distance.
Yes. So have you ever seen this kind of, so what does pi stand for?
Isn't it? I thought that's back to like the parent node. Or
Yes,
something.
parent node, yes. So have we seen this kind of operation before?
Yeah, that's in BFS.
Yes. See, this is the BFS function. For each node, U will associate with the distance that is infinity, and we associate with the parent that is new. So pretty much the same. So that's why we call it initialize. So we usually call, we only call this function in the beginning of the search algorithm, okay? So we call this function to initialize our search process. So this is because before we do any search, we just assume that from and so basically what this function does is that it associates each node with a new parent, and for any node that except for the source, it associates it with a infinity distance, whereas for the source node, it associated with a zero distance. Okay, so do you know why do we associate a zero distance for the source node?
That's where you're starting at?
Say it again.
That's where you're starting at?
Yes. So I think we discussed this problem before. In the BFS algorithm, we also have the same operation, s dot d equal to 0. We associate 0 distance for the source node. So the main reason is that if I ask you, I think I asked you this question before, what is the minimum distance from your home to your home?
It would be 0.
Yes, same as here, okay? So because the source node is S, so what we know is that from the source node to the source node itself, the minimum distance must be 0. We don't need to travel any distance. So that's why we do it. But for all the other nodes, because we haven't started the search yet, so we just assume that the distance is infinity, meaning that from the source node, we cannot reach. We just assume that we cannot reach all the other nodes. Make sense?
Yes.
Okay. So this is what we do. Basically, in the initialize function, for each node except for the source node, we associate with the infinity distance, but we only associate the source node with a 0 distance because the minimum distance from the source to the source is simply 0. Any question with regard to this function? No? Okay. So let me say, okay, and then we need to discuss another function, relax. And this function is a little bit more difficult, okay? So I'm going to use an example to explain that. So suppose this is our destination. We want to go to Montclair. We want to go to campus, okay? And then this is your home. Okay, and this is another place. Let's say, for example, this is Clifton. Okay, so if say without Clifton, we know that, okay, so from your home, if you drive directly or through any road, so you just pick a route, like for example, this way. So this route, this purple route may go across many, a few different places like Natalie, like even your work or whatever place. So this is just a route. You can think it as a path that Google just showed you. Okay, Google Map just showed you. Okay, it tells you, okay, from your home, if you follow this route, so so you will be able to get to Montclair with 1.5 hours. Okay, so and then you open up your map again, your Google Map again. You say, okay, what if I just want to go to Clifton first and then go to Montclair? Because we know that there is a direct road that connects Clifton to Montclair, and this road only takes you 0.5 hour. Okay, so for example, we have road 3 that connects Clifton and Montclair and directly. this is just an edge or direct road. And here, so this road takes you around 30 minutes. And at the same time, okay, Google Maps tell you, okay, so I just find a route from your home to Clifton that takes you 0.5 hours. Okay, so from this two, so basically here you got two choices. Either you follow the purple route that takes you 1.5 hours, or you follow the blue route to go to Clifton and spend 0.5 hours, and then from Clifton you just follow Route 3, and directly. So there is a Route 3 and which directly connects Clifton to Montclair, and so you need to spend another 0.5 hours on it. So which one do you want to? Which route do you want to follow?
Clifton route.
Say it again.
The Clifton route.
Yes, we definitely prefer this route, right? So let's say previously, if Google only presents this road for you, in your mind, the shortest distance from your home to Montclair is 1.5 hours. But if you take Clifton as the last stop that you need to make before going to Montclair, basically it's like you take a detour, and and this route gives you 1 hour. So we definitely prefer this route, correct?
Yeah.
Okay, so this is what does this function do. So here you can take V. So this function, relax function, takes three inputs. That U, V are a node, a pair of nodes, and in the graph there is a road from U to V. There is there is an edge from U to V. So for example, here you can take Clifton as U and Montclair as V, because there is a direct route that connects. There is a road or an edge a single road that connects Clifton with Montclair, and W is the weight function, so which tells you the weight of this edge. So basically, for an edge from U to V in the graph, if there is an edge from U to V in the graph, we can call the relax function. What this relax function does is that, so what it does is that if V dot D is larger than U dot D plus WV, V dot D is basically the minimal distance from home to Montclair that has been V dot D is basically the minimum distance from the source node, which is your home, to the node V that has been found. So suppose that this is, for now we just ignore this the blue road. We just ignore the blue route, and we only focus on this purple route. This is what Google Maps shows to you. Okay, so Google Maps shows you, okay, so based on my search result, so far I found that the best route to go from your home to Montclair is this route, and it's going to take you 1.5 hours. So in your mind, for Montclair, the minimum distance from your home is going to be 1.5, correct?
Yep.
Correct.
Okay, and then so you know that, okay, so also Google Maps shows you, okay, from your home to Clifton, the best route gives you 0.5 hours. So for this node, for Clifton, U dot D is 0.5. Okay, and so this is WUV. WUV, the road that connects to let me make it a little better. So I'm not going to use 0.5. I'm going to use another one, 0.8. And so U dot D is 0.8, not 0.5. Okay, so this route is 0.8 hours. So U dot D is 0.8, and this route 3 is going to take you 30 minutes to go from Clifton to Montclair. So the weight of this edge between U and V is 0.5. Okay, so So here, what we do is that, okay, so far the best route we know is this, and it gives us a distance of v dot d as 1.5. So here we got v dot d as 1.5. And here is another route, an alternative route that we just find, and in which we are going to make a detour at Clifton. This detour road, the total distance of this detour road is going to be the minimum distance from the source node to U, which is 0.8, plus this road, the time that you are going to spend on this road directly, 0.5, correct? Am I correct?
Yes.
So here you are comparing the direct route, the distance of the direct route and the detour route. So what do you find? So if the direct route takes more time than the detour route, we are going to prefer the detour route, correct?
Correct.
Okay, so so that's why we have this if statement. If this is large, v dot d is larger than u dot d plus wv, we're going to set v dot d as this 0.8 plus 0.5 as 1.3. So we change this value, we reduce it to 1.3. So we say, okay, so far we find a better route, which is to make a detour at Clifton. And because the total distance, the total travel time is going to be 1.3 hours, which is less than 1.5. And then we're going to set the parent of V or the parent of Montclair as Clifton. It means that, okay, so it means that so the best, if you so far the best route to reach if you want to go to Montclair, the best route is to go to Clifton first. It means that the parent, so here we set the parent of Montclair as Clifton. It means that before going to Montclair, you should arrive at Clifton first. Make sense?
Yeah.
Okay.
Good.
So
Yeah.
what this, cool, thank you. So what this relax function does is that it's going to find, so it is going to find one edge in the graph and to say, okay, if we make a detour at U, tries to reduce the minimum distance to V by making a detour at U. Okay, if by making a detour at U, we can save the travel time, then we prefer that we will make the detour. Otherwise, we will stick to the original route. So for example, if this road is not 1.5 hours, it's just 1 hour. So we definitely stick to the purple route. Okay, so make sense?
Yep.
Okay, and here you can see that the relax function, if this if condition is evaluated as true, then basically we are going to add this edge into the shortest path from the source to V, right? So if this is successful, then we are going to have this edge, the road 3, or the road the edge between U and V included in the shortest path from the source to V. Okay, so basically, so if we want to use one sentence to summarize the relax function, okay, try to reduce V dot D by making a detour at U and including the edge from U to V in the shortest path. Okay, they will say if we include this edge in the shortest path, if it can help us to reduce the total distance, then we will do that. So this is a brief summary of what we do for the relax function. Okay, so any questions so far?
questions.
Okay, cool. So also here, if no question, I want to ask you a question. What is the complexity of the initialization algorithm?
Of n.
OV.
OV, I mean OV. Yeah.
Yes, OV. V is the number of nodes in the graph, because in this function we only have a for loop, and we're going to do something for each node in the graph. So the total complexity is going to be linear to the number of nodes in the graph. And what about this one? What about the relax function? What is the complexity?
Is that also OV?
No, it's going to be O1, because
O1?
in this function, we don't have any for loop. We don't have, basically, we don't have any loops. And also we don't make any other function calls. So if this is true, then if this statement is true, then we're going to execute 3 instructions. If it's not, if it's false, we're going to only execute 1 instruction, right? So the total, the number, the amount of instructions that we're going to execute is independent from the size of the graph. So that's why we have a O1 complexity for the relax function.
So it doesn't matter how many like vertices you visit, just like
No,
doesn't-
because here we're only going to call this function for a single edge from U to V, right? So this is the complexity for a single edge.
Okay.
Okay, cool. So and then next I'm going to talk about something that is a little bit not fun for you, or yes, it could be fun. So far it could be fun. And okay, so there are some factors that we need to consider when we are doing the single source shortest path search. So the first factor that we need to worry about is that whether is there any edge that comes with a negative weight. Okay, so here, because previously we are talking about the travel time, so how much time are you going to spend on a road? And so if we say, okay, if you want to travel from like city A to city B, place A to place B, if I say, okay, it's going to take you 0.5 hours, negative 0.5 hours, you must say, okay, are you crazy? So it's not going to, we cannot have negative time, right? But if we use, that's because we use the edge weight to represent the travel time. However, if we use the edge weight to represent something else, then there could be a negative edge weight. So for example, so is there any one of you who are using credit card? Yes or no?
Yeah.
Yeah, okay. So do you think it's a good thing or bad? What's the main reason for to use a credit card?
Build up your credit.
Say?
Yeah.
Oh yes, to lift the credit. So you want to build your credit so that in the future, if you want to make a major purchase like buy a house, then your interest rate can be lower, right? That's very smart. And is there anything else?
It's like, so if you don't have like the money like at that time, you just use the money.
So it's like you can just like spend early. So you can spend the money that you have that haven't gone to your pocket yet. Okay. What is there any other reason? How about cashback? Do you know there is a cashback?
Oh yeah,
for
you can do that.
credit card?
Like whatever you spend, you get like 5% cash back on it. Something like
Yes, 5%, 2%, 3%, whatever. Okay, so so here, yes, it's pretty good if you want to say use your credit card as to build your credit, also for the cashback, but don't go this way. Do not spend early. Do not spend the money that you cannot afford. Do not spend the money that you cannot pay back in the full amount in when it is due, not just the minimum. You need to pay, you only use the credit card if you're sure that you can pay it in full in the next so due date. Okay, do you know why is that? It is because if you spend early and you don't pay it in the full amount, you know how much interest are you going to pay to your credit card company?
Yeah, there's like 20%.
Around 30%. The US allows the credit card company to charge you anywhere from as long as it's below 33%, it is protected by law. Okay, annually, they charge you an interest rate of 30%. That's crazy. I mean, the best investment. I think I talked about that before, right? The best investment channel is to invest on yourself. How much investor rate? How much says interest rate, or how much says growth rate can you get from investing on yourself?
An infinite.
20%. Okay, if you go to school for 1 more year, you are going to increase your salary on average by 20%. But say, so this is way larger. 30% is way larger than 20%. It means that you are only going to lose money if you want to spend early. Okay, so never do that. Use your credit card as if it's a debit card. Whenever you spend something, just pay it back in the full amount once in the next due date. On the next due date, don't just pay the minimum. You are going to screw yourself up with that. You are going to fall into a cycle where you cannot even, you are just opening a new credit card to pay for your current credit card's minimum payment. Don't do that. You will lose your life. Okay, so that's just my personal advice. This is really important. It's even more important than our lecture. Don't do that. A big no to this. Okay. So personally, yes, these two things are great. For me, like I love to travel. Every year I travel 2 or 3 times. I rarely spend money out of my pocket. Instead, I just use the cashback from my credit card to pay for my travels. So you can also take advantage of that. So here, let's say if this is you and this is a bank, say Chase or Bank of America. If you use the credit card, let's say your credit card gives you 5% cashback. Do you know what does that mean?
Every dollar you spend, you get 5% back.
Yes. So let's say if you spend $5, sorry, $100, then Chase is going to pay you $5. It means that, okay, so when you spend, so here we use the edge weight to represent the cash flow for yourself. So if you pay Chase, sorry, the cash flow for the bank Chase, if you pay Chase $100, pay $100 through Chase, then Chase will return you $5. So here we got a negative edge weight, which represents that. So Chase is going to return you $5. So Chase is kind of like going to lose $5 if you spend $100, but actually they make money from that because of this 30% investment interest rate. So the credit card company offers you the cashback just to motivate you to open up a credit card with that bank, and they bet that you're going to fall into that cycle and pay them 30% interest every year. So so it looks like they pay you a 5%, but actually they bet that they can make 25% from you. And so it's a dirty business. Don't do that. Okay. So here, as we can say that we can have negative weights in the edges, but there is one thing. So this is okay. Negative weights is okay, but negative cycles are not going to be okay. What does negative cycle mean? So, for example, if someday Chase said, I'm going to go crazy. I'm not going to give you 5% cashback. I'm going to give you 105% cashback. Okay, it means that every time you lose, every time you spend $500, sorry, $100, Chase is going to return you $105 back. So if someday this happens, don't know what are we going to do. If you got a credit card with 105% cash back, so don't know how can you be rich.
Spend
Yes, just keep spending. Buy a whole masses. You just need to go to masses. Do not just buy a clothes or a pair of shoes. Just buy the whole masses, because the more you spend, the more you earn. So every time you spend $100, actually you got $5 in your pocket as the revenue. Correct?
Yep.
So as you can see that if there is a 105% cashback rate, then this cycle, the total weight in this cycle is going to be -$5, right? Correct?
Yeah.
It means that every time when you spend $100, Chase is going to lose $5 from their money. And so the more the people spend, the more Chase lose. So if everybody is just going crazy shopping, and Chase is going to fare their bankruptcy very soon. So this is going to be problematic. Okay, so when we are doing single source shortest path search, we allow negative weights in the graph, but we cannot allow negative cycles, because negative cycles means that there is a problem with the design of the graph. This is not going to be okay, like the 105% cashback. Okay, just keep those things in mind, those two things in mind, okay? Any question with these two factors? No? Okay, so then before I present the Bellman for the algorithm, I want to discuss the plan for the rest of the semester with you. So so here we are at let me just use this one. No, let me just use this one. Okay, so we are in the week of April 30th. I'm going to use the Friday as the week to denote that we're in the week where the Friday is April 30th, and then it's going to be May 7th, May 14th, and May 21st. So May 21st is the end of our semester. We need to finish everything by that time. Okay, so and currently we're in this week. Currently we're in this week. So it means that including this week, we have 4 weeks to go. And so my plan is that, okay, so in this week, I'm going to talk about the single source shortest path. Single source shortest path problem for you. And you have your homework 10. Your homework 10 is going to be due on this day, on May 7th, okay? And the next week, I'm going to present another topic for you. It's called all pair shortest path. It's a new topic, and that lecture is going to be relatively short. So I'm first going to present the all pair shortest path one for you, and then using one lecture to present this algorithm for you, and then you will have your final project. So your final project is the same as basically the same as a homework, but there is no skeleton code. You're on your own, okay? So and in the final project, you are allowed to collaborate with at most 2 students. It means that each group can have at most 3 students, but it's totally fine if you want to do it by yourself. And the final project is going to be due on this date, May 21st. So literally you have 2 weeks to work on your final project. And also next Friday, I'm going to talk about the final exam review, okay? So I'm going to help you go over the things that I want to discuss for the so you will have your final exam, okay? And then on May 14th, so sorry, in the week of May 14th, we should have 2 lectures on Tuesdays and on Fridays, okay? On that Tuesday, we're not going to have any lecture because I'm going to give you that Tuesday as a time for you to prepare for your final exam. And on May 14th, we're going to have our, which is the Friday, we're going to have our final exam. Okay. So and then after the final exam, you have 1 more week to finish your final project and submit on May 21st, by May 21st. Does that sound good?
Yeah. Yeah, it does.
Okay. So you can see here, from the final review to final exam, you have 1 week to get prepared. So the thing I'm going to assure you is that the final, you don't have to prepare a lot of things for your final exam. So to get prepared for your final exam, I want you to spend only 4 hours preparation, not the exam time, on preparation. And the final exam is only going to be 75 minutes long of the exam. Okay, so it's not too difficult. So the reason why I make I let you take the final exam before the so 1 week before the end of semester is that I want you to take the final exam when you still have a fresh memory about the topics that we have discussed. And so you don't have to spend a lot of time. If I give you 2 weeks, if there is a gap of 2 weeks between our last lecture and the final exam, you will lose the memory of a lot of things, and it will only make your preparation longer. Okay, so this is the plan for the rest of the semester. And I got 1 question from the chat area asking me, so is the final exam going to be multiple choices? No. So this is the final exam is more like my pseudocode thing. Okay, so for example, like what I discussed in last lecture, like for example, the prim algorithm, I will give you the pseudocode, give you an example. I want you to list the steps for you to run the code over the example, and this will show you that, demonstrate that you understand the algorithm very well. So no multiple choice. Okay. So any question regarding the schedule or regarding the plan for the rest of the semester? I'm not sure if I explained it in a clear way. So if you have a question, just ask it.
Professor, can I ask you something?
Oh, can you speak a little bit loudly?
Professor, can you give us like a sample before the final exam so we know what to expect when we are gonna have the final exam, like a sample quiz so we can do it at home?
Okay, so if you want a sample quiz, I can show it to you now. Okay, just wait a second. This one, yes, the sample quiz is like this. I give you for example, I give you the LCS pseudocode, and I give you an input string, a pair of input strings. I ask you to write down the content in the 2 tables. That's a good sample, right? Yes, it's going to be in this format. I'm going to give you the pseudocode, an input example, and I want you to write down the something like the intermediate procedures. For example, how does the matrix look like? And if you got this correctly, it means that you understand the pseudocode very well.
Okay. Thank you, Professor.
No problem. So,
Hey, Professor, quick question.
Mhm.
Is the final exam cumulative? So is it like everything that we went over so far in the course?
yes, it's going to cover all the topics that we have discussed. So basically, if our class includes 4 different chapters: sorting algorithms, basic data structures, and then dynamic programming, and then graph, right?
Oh, yeah.
So we got 4 chapters, and then in the final exam, you are going to have 4 questions, and each question corresponding to 1 chapter.
Okay. Gotcha. Thank you.
Okay, so make sure that you come to my class next Friday, because I'm going to help you to have a final review for you, and this final review will save you the preparation time dramatically. Okay, so if you have a friend who does not come to my lecture regularly, let your friend know he or she had better come to my final review lecture next Friday. So with that final review, if you pay attention to that final review lecture, you are going to be able to finish your preparation within 4 hours. Otherwise, it's going to be something like 15 hours. Okay, so any other question?
What's the percentage of the final exam? Like, how much is it on our total grade?
I think it's 20%. Let me check the syllabi. So yes, 20%.
Okay, thank you.
No problem. So each homework is around 7%. Each homework is around 7%. The final project is 10%, and the final exam is 20%. So yes, it's very easy to calculate your final grade after the exam. So there is going to be no curve. And your grade is going to follow this table. Okay. And any other question for me? Okay, so then if no question, I'm going to talk about the Bellman-Ford algorithm. So the Bellman-Ford algorithm it's not that difficult to understand. You just need to understand the logic, and to implement that it's super easy, very easy. So the Bellman-Ford algorithm allows the negative weight cycle in the graph. So previously we say that if we got an input graph that has negative weight, it is absolutely fine. But if there is a negative cycle, it means that the input graph is arrow. There is an arrow in the input graph. It's wrong. So what Bellman-Ford algorithm does is that even though you send it with a incorrect graph that includes a negative cycle, it is able to run, and it can detect the existence of the negative cycle. It will output false, and false means that it's a signal to you saying that, okay, dude, your input is wrong. It has a negative cycle. So this is the power of that. So it even works with incorrect input graph. And the key idea behind the Bellman-Ford algorithm is that a shortest path can contain at most a shortest path contains at most n nodes that are connected by n-1 edges. So for each destination, relax it n-1 times. Let me explain this for you, okay? So suppose here I'm going to list a couple of cities from the northmost place to the southmost place of the east coast. So for example, this is Boston. This is New York. And we have DC, we have Atlanta, we have Orlando, and we have Miami. Okay, so these are the cities on the east coast from the northmost place to the southmost place. Okay, suppose here I'll ask you to go from Boston to go to Miami. Okay, this is your south and this is your destination. I use T to denote destination. This is the southmost side. Okay, so how are you going to travel? So you may say, okay, how are you going to drive to Miami? You may say, okay, I will just go from Boston to DC directly. Suppose there is a road that connects Boston to DC directly, and then make stop at Atlanta, and then go to, and from Atlanta, I'm not going to make a detour at Orlando. I'm just going to drive directly to Miami, right? So is this a possible route?
Yeah, it's possible.
Yes. Or some of you may say, okay, I want to visit all the places, so along the road. So first I want to go to visit the New York City, and then go to DC, and go to Atlanta. So I'm going to visit all these cities, and finally I will make it to Miami. Okay. So this is also possible, right? And is it so if someone, let's say this, okay? What if someone just come through this plan? Okay, I'm going to make, so go from Boston to DC first, and then come back to New York City, and then go to DC, and then go to Atlanta, and then go to Orlando, and then go to Miami. Is this a good plan?
No.
No.
No, because you are, even though by following the blue colors, you are able to visit all the cities, but what you do is that you actually spend more time on the road, right? Because you are commuting between New York and DC twice, and you don't move by making a cycle over here. You don't make any progress. Correct? Yep,
that's correct.
Correct.
Okay, so this is not going to be okay. This blue route is not going to be okay. So the reason why I want to use this example is that in a short, if we get say 1, 2, 3, 4, 5, 6, if we got 6 nodes, so here the blue path, let's say how many cities do we go across by following the blue path? So if we start with one node at Boston, and then we'll come to DC 2, 3, go back to DC first, again 4, 5, 6, 7. So the blue nodes travels 7 nodes, and to connect these 7 nodes, there are how many edges? 1, 2, 3, 4, 5, 6. There are 6 edges. Okay, so here the blue nodes basically repeatedly visit the same place twice. The same place are say DC. We visit DC twice, and it wastes us time. So what I want to say is that, okay, so if we check the green line, the green route, how many nodes do we go across? 1, 2, 3, 4, 5, 6. So the green one travels 6 nodes, And how many edges are there to connect these 6 edges? 1, 2, 3, 4, 5. 5 edges. Okay. So a valid path, or a path without traveling the same place multiple times. So if we have 6 nodes, and then the path, so the shortest path will include at most 6 nodes and 5 edges. Am I correct?
Yes.
Yes. So if let me be general. Okay, if we have n nodes, then a shortest path can have at most a shortest path. If we have n nodes, shortest path can have at most n nodes and n-1 edges to connect these n nodes. If there is more than n nodes, do you know what does that mean? Included in a shortest path, in a path. Do you know what does that mean? It means that we repeatedly visit the same place twice, and it means that we have to make a cycle and waste our time on in that cycle, like what we do over here. We repeatedly visit DC twice, and we waste the time over here. So a shortest path, if we are given a graph with n nodes, then a shortest path can have at most n nodes and n-1 edges. Okay, this is a little bit mathematical, but if you don't understand it, it's fine. Just keep that in mind. Okay. So the logic of the key idea of Bellman-Ford algorithm is again going to related to the relaxed algorithm. Let's say, what do we do in the relaxed algorithm? In the relaxed algorithm, what we do is that we try to reduce the shortest distance by making a detour at the node U, and including the edge in the shortest path. Correct?
Yeah.
This is what we do with the relax function. We try to include an edge in the shortest path, in the shortest path. So, and also at the same time, we know that a shortest path can include at most n-1 edges, right? So then the Bellman-Ford algorithm, what we do in the Bellman-Ford algorithm is this. First, we call the initialize function to say, to set we initialize it. And this is the most important part. So, okay, this is the most important part. For I from n g dot v minus 1, g dot v is n, the number of nodes in the graph, Then for each edge in the graph, we call the relax function. It means that since a shortest path can include at most n-1 edges, so it's like we have at most n-1 spaces, and then for each edge, we're going to say, okay, call the relax function at first. We're going to call the relax function for each edge at the first place to say, okay, if any edge should be put over here, and next time in the next iteration of the outer for loop, we're going to target on this one. We're going to say if any edge should stay in this space, and then if in a say third iteration of the outer for loop, we are going to try to fit an edge in the third place. So in that way, we can get the shortest path down. So the key idea is that since a shortest path includes at most n nodes and that are connected by at most n-1 edges, so for each destination, we are going to relax it at most n-1 times. So this is what we do for the the main part of the Bellman-Ford algorithm. I know this is very mathematical. It's fine. It's absolutely fine if you don't understand it. It's fine. You just need to go back home and implement that. When you implement this and when you see the final output, you will be able to understand it. Okay. So and then what we do in the so here we have one more for loop. This for loop is that we are going to reduce it one more time. If we are able to successfully reduce it one more time, if this condition is true, it means that there is a negative cycle. So it means there is a negative cycle. So here, from line 2 to line 4, we are building the shortest path. We're just built the shortest path. From line 5 to line 7, we'll detect the negative cycle. If there is any negative cycle, the algorithm will return false. It's like a signal sending to you saying that your input is wrong. Otherwise, it will return true, meaning that I successfully finished my run, and I have already found all the shortest paths, and also there is nothing wrong with your input graph. Okay, so this is what we do in the Bellman Ford algorithm. You just need to know the key idea of that, of the Bellman Ford algorithm, and go back to home to implement that in your homework, and you will be able to understand it, very good manner. Okay, and I'm not going to use an example to show the detailed steps because it is just there are just too many steps, and all of us will be lost. So in that procedure. And the last thing that I want to discuss about the Bellman Ford algorithm is the complexity. Its complexity is this, OVE. The number of nodes times the number of edges. This is because in this for loop, how many iterations do we repeat in the for loop in the second line?
The amount of edges.
Amount of edges. Sorry, the amount of nodes minus 1.
No,
right?
yeah.
How many for loops do we repeat in the third line? How many iterations are there in this for loop in the third line?
The same.
E, because for each edge in the graph, we need to have 1 iteration. So in the upper line, for each node in the graph, we need to have an iteration. So because these are nested loops, so we need to multiply them. So that's why we got the time complexity as this, V minus 1 times E. And here we can just ignore the constant 1. And so then we end up with OVE complexity. The number of nodes times the number of edges in the graph. Okay, so yes, that's all I want to discuss for the Bellman Ford algorithm. Again, you just need to keep in mind what is the key idea behind Bellman Ford algorithm. And when you are doing your homework, there is almost no difficulty with this. You will not almost have no difficulty with this algorithm. It's relatively simple for you to implement. Okay, so any question for me?
No questions.
No? Then yes, that's it. And have a good day.
Thank you, Professor. Have a good day.
Thank you.
Good one, Professor.
Thank you.